Hello, everyone. Welcome back, and thank you for joining me today. If you're new to the channel, please make sure you subscribe so you can get more notifications and like this video if you like it. In this video, I'm going to teach you how to write molecular, complete, and net ionic equations for acid-base reactions. So for this particular video, we're going to go over potassium cyanide reacting with hydrochloric acid. So let's get into this. So as you can see, we're given the names instead of the formulas. So you're going to have to know the names of the substances. And so you need to know how to go from the name to the formula. And so if you're kind of rusty with that, and if you're not sure how to do that, I have a video that goes over naming ionic compounds. I also have a video that goes over how to name acids, so you can see those videos. I'll link those videos in the description. So we need to convert this into a formula. So here, potassium cyanide is an ionic substance, so we can go backwards by understanding that the name of the substance comes from the name of the ion. So if you know the names of the ions, you just put those together and you've got the name of your substance. So in this way, we're working backwards. So each part is an ion name. So potassium ion and cyanide ion. So we need to write the formula or the symbol. So for potassium, it's a K. And we know that potassium has a +1 charge. How do we know it has a +1 charge, you ask? Well, one way we know is if we know the rule that for elements in the 1A, 2A, or 3A main groups, then the positive charge of that element is equal to the group number that it's in. So since potassium is in group 1A, therefore it's going to have a +1 charge. If the element is in group 3A, it would have a 3+ charge. If it's in 2A, it would have a 2+ charge. So that's how I know it's a plus charge. Also, the better way to understand this or know why it has a plus charge is because of the valence electrons and that the fact that all atoms want to be like noble gases. So they're going to lose and gain electrons in order to be like the noble gas. And how do they want to be like noble gases? Noble gases have a completed outer shell, a valence shell. And so they're going to lose or gain electrons in order to have a full shell, which is usually 8. So since potassium is in group 1, we know it has one valence electron. And so we know that because the rule is if you're a main group element, the number of valence electrons you have is equal to the group number you're in. So since this is in group 1A, then it has one valence electron. If it was in group 7, it would be 7 valence electrons. If it was in group 4, it would be 4 valence electrons. So that's how you know. And so since this has one valence electron, it's really easy for potassium to just lose that one electron. And so that way it would now have that outer full shell. And so by losing that negative electron, it now has a proton that no longer is balanced in charge. So that one proton gives a positive charge to the atom. So, excuse me. So we have the potassium ion. Now what about cyanide? Cyanide is a polyatomic ion. You need to know your polyatomic ions. You need to know the formulas and the charges. I'm sure your teacher has given you a sheet or a table of polyatomic ions for you to memorize. I have a video that goes over an easy way of memorizing and helping you see patterns in the different polyatomic ions, so it helps you memorize them more easily. So I'll link that video in the description section as well. So also, so with regard to cyanide, we know that that has to be Cn minus. So now we have the formula for Cn minus and the potassium. We're going to put those together to form the formula. And so when we put those together, we need to make sure that the charges are balanced. And so we have a +1 charge, we have a -1 charge. That's a 1-to-1, so we only need one each. So we can just put that together as KCN minus. Oops, we don't write the minus for the formula. So another way you could do it is do the crisscross method. We have 1 here, we have a 1 there. This could go as a subscript. This could go as a subscript on that side. So we crisscross. We don't write the 1s in, but you get the same answer. All right, so here we have our first substance, and then hydrochloric acid. We need to add that. So hydrochloric acid, you need to know how to name the acids. So right away, when you look at this name, you should be able to identify this as a binary acid, not an oxyacid. So binary acids, they begin with the word hydro. Hydro refers to hydrogen. So binary acid means you have two two ions, or two ions that are together. Not polyatomic ions, but there is an exception. We're not talking about, this is going to be distinct from your oxyacids that have the polyatomic ions, like that have oxygen in them, like your chlorate, your chlorite, your sulfate, sulfite, phosphate, things like that. So here we have hydro. Hydro refers to hydrogen. That's going to be the one element. And then chloric is referring to chlorine. So that's going to be your second element, binary, 1, 2. So here it's going to be H for hydro and Cl for chlorine. And so H has a plus charge, the chlorine usually has a -1 charge. So we have a 1-to-1 relationship there. This is not an ionic substance. It is a molecular substance that happens to ionize into ions when it's put into water. So be careful of that. So now we can figure out the products. And so we have an ionic substance here. We have a strong acid here. This is going to ionize into your ions. So we have two basically ionic substances. This is not an ionic substance, but it's like an ionic substance. So whenever you have two ionic or ionic-like substances, this would be a double displacement reaction. So that's a dead giveaway. So how do you find the products for a double displacement reaction? Well, you take the ions in the inner part, you put those together, and you take the outer ions and you put those together, and you form your formulas from there. And again, when you write the formula, you got to balance the charge. So potassium has a +1 charge, chloride has a -1 charge, so that's 1-to-1. So I need one each, KCl. And then for the inner ones, I'm going to have H and Cn. H is a +1, Cn is a -1. So again, it's going to be 1-to-1. So HCN. And now I have my completed reaction. And so now I can balance the equation and write the states of matter. So let's balance the equation. I have 1 potassium, so that's balanced. I have 1 cyanide ion, I have 1 cyanide ion, that's balanced. I have 1 hydrogen, that's balanced. And I have 1 chloride ion and 1 chloride ion. So this is all balanced. Great, that was easy. So now we have to figure out the states. So potassium cyanide, is that going to be soluble or insoluble? So we can use our solubility rules for this. So you can find that on the internet, or your teacher probably gave you a sheet, or it's in your book. So if we look up, let's see, it says all salts of group 1A are soluble. Ammonium ion is included here. So anything with the ammonium ion or anything with group 1A elements are going to be soluble. And we have potassium, which is a group 1A element. Therefore, this is soluble. So it's AQ, aqueous. We said that hydrochloric acid is a strong acid. That means that it dissociates completely in water. That's opposed to weak acids. Weak acids don't really separate into their ions, or doesn't ionize very easily or very much at all. So this is going to be aqueous. even if it didn't, even if this is a weak acid, it would still be aqueous because we're assuming this is dissolved in water. But we need to keep in mind that this is going to separate into its ions completely. Again, we have KCl. This is going to be aqueous for the same reason. Chlorides are aqueous unless they're paired with the metals silver or lead 2 ion or the mercury 1 ion. Um, your group 1 elements are all soluble. So this is going to be aqueous. And we have HCN. So you should recognize this as an acid. And it's going to be, this is hydrocyanic acid. Now it's called, it's named like a binary acid, but you'll notice that there's more than one element here. So we're treating this as kind of a one part here. It doesn't have any oxygen in it, so it's not an oxyacid. So we kind of name it like a binary acid, even though binary means two. And so we have 2 ions, but we don't have 2 elements. So this is going to be your HCN. So now that we have that, so this is your balanced molecular equation. Okay, so let's continue with this. Okay, so now that we have that, we're going to need to write our complete ionic equation. So what do? When you're writing your complete ionic equation, all you're going to do is separate everything into its ions. That's going to separate into ions. So we know that this is aqueous. That's going to separate into its ions. This is a strong acid. That's going to separate into its ions. This is aqueous. This is soluble in water. So that's going to separate into ions. And this here is a weak acid. So this is not going to separate into its ions, but it's going to be aqueous. So hydrocyanic acid is one of the weak acids. It's not one of the 6 strong ones that you need to know. So it's a weak acid. So this is really going to stay together. This is not going to really separate into separate ions. It will a little bit, but not very much. So we're going to keep that together. So when we write our complete ionic equation, it's going to look like this. So it's going to be K plus aqueous plus Cn minus aqueous. And you'll notice that when I separate the ions, I'm writing the charges. When we have it as a substance, when we write the formula together, we don't write the charges in the formula, only when we separate them. And so now we can do your hydrochloric acid. So that's going to be H plus aqueous plus Cl minus aqueous. And now we can do the products. So this is going to come apart. So that's going to be K plus aqueous plus Cl minus aqueous plus, and then this is going to stay together. That's going to be HCN aqueous. And so this is our complete reaction, complete ionic reaction. Everything has been pulled apart into its ions except for the HCN, which is a weak acid. That's going to stay together. So now for our net ionic equation, we need to figure out what the spectator ions are. So we're going to remove the spectator ions from the complete ionic equation to make your net ionic equation. So this is kind of like taking taxes out of your paycheck. Your net pay is what you get after taxes are removed. So we're going to get our net ionic equation after the spectator ions are removed. So what are the spectator ions? The way we can do this, the way we identify the spectator ions is twofold. First, you might look at what the product is. So what's staying together? So we might think of this as a product. Our weak acid is staying together. And then so we could figure out, okay, well, what 2 ions are forming that product? And then those are not spectator ions. The others would be spectator ions. The other way would be to look at what stays the same on both sides. And this is probably a better way to figure it out. So here, I notice that K plus is aqueous on this side. And on this side, in the product side, it's still K plus aqueous. So there's no change. So this is not participating in any reaction. So that is a spectator ion. So we could get rid of K plus. What about Cn minus? Well, Cn minus aqueous is here on this side, but you'll notice it's not Cn aqueous over here, it's HCN. So Cn aqueous or Cn minus aqueous is no longer on this side of the equation. So this would be a player. So this is part of the reaction, so not a spectator ion. Same thing for the hydrogen. H plus aqueous here. There's no H plus aqueous here, so that is part of the reaction. Chloride ion aqueous here, chloride ion aqueous here, same on both sides, so that is a spectator ion, so we can get rid of that. And so now we've gotten rid of our spectator ions, so now all we need to do is write everything else. So here we have Cn minus aqueous plus H plus aqueous, and that's going to give us, oops, I forgot to cancel out the chloride ion there. And that's going to give us our HCN aqueous. And that would be our complete reaction. Now, our net ionic reaction, excuse me. So this is a weak acid. So really, this actually is reversible. And so if we wanted to write this as a reversible reaction, most of our substance is going to be in this form. This is not going to separate into ions very easily. So you'll get a little bit of this in water in solution, but most of it, by and large, this is what you have in solution. So if we're going to write this, maybe a longer arrow on this side and then a smaller arrow going backwards, indicating that most of your substance in water in solution is going to be this. Some of it will be this. So I hope this is helpful. If you liked my video, if you learned something, if you learned something you didn't know before, then please hit the like button. Please subscribe to my channel so you can get notified with other videos that I will be putting out. So hit that notification bell right there. Put a comment in the comment section. Let me know what you think. And if you have any other questions, please ask. Thanks for joining me. Have a great day.